this video, we'll see how a CPU actually executes a program. To keep things simple, we'll use a 32-bit MIPS processor as our example. While modern processors are much more complex, the fundamental ideas are very similar. At a high level, a CPU executes instructions in 5 main stages: fetch, decode, execute, memory, and write back. Every instruction that a program runs passes through these stages. During fetch, the CPU retrieves an instruction from memory. During decode, it figures out what that instruction means. During execute, it performs the required operation. During the memory stage, it accesses data memory if needed. Finally, during write back, the result is stored back into the processor. Before we begin, it's useful to know that MIPS instructions are grouped into 3 main formats: R-type, I-type, and J-type instructions. R-type instructions are used for register-to-register operations such as add sub and or SLT. For example, add T2, T0, T1. I-type instructions contain an immediate value and are commonly used for arithmetic, memory access, and branching operations such as add immediate, load word, store word, branch equal. J-type instructions are used to change the flow of execution and contain a jump target address, such as jump and link. Although these instructions perform different tasks, they all move through the same processor pipeline and use many of the same hardware components. To understand how all of this works, let's follow a simple R-type instruction. Add T2, T0, T1. As it moves through each stage of the processor, everything begins with a small but extremely important component called the program counter, or PC. The program counter, or PC, is a 32-bit register that stores the memory address of the next instruction to be executed. A register is built from flip-flops, and each flip-flop can store 1 bit of data. Instruction memory is the part of memory that stores a program's machine code instructions. During the fetch phase, the address in the program counter is sent to instruction memory, which returns the instructions stored at that location. Simultaneously, the PC is sent to a 32-bit adder that adds 4, generating the address of the next instruction. The program counter is then updated with PC plus 4, ready for the next fetch cycle. The fetched instruction now enters the decode stage. But before we decode the instruction, let's first understand another important component of the processor, the register file. The register file is a small high-speed memory inside the CPU that contains 32 registers, with each register capable of storing 32 bits of data. These registers hold the values that instructions operate on. Now suppose the fetched instruction is add T2, T0, T1. The first step in decoding is to break the instruction into its different fields. The processor extracts the opcode, source registers, destination register, and any other required information. The opcode is sent to the control unit, which determines what operation needs to be performed. In this case, the control unit recognizes that this is an ADD instruction. At the same time, the register fields are sent to the register file. The instruction specifies T0 and T1 as the source registers and T2 as the destination register. The register file then reads the values currently stored in T0 and T1 and places them on its output ports. By the end of the decode stage, the processor knows exactly what operation it must perform, where the input data is located, and where the final result should be stored. The values from T0 and T1 are now ready to be sent to the execute stage, where the actual addition will take place. With the instruction decoded, and the values from T0 and T1 retrieved from the register file, the processor now moves to the execute stage. For our example instruction, add T2, T0, T1. The control unit has already determined that this is an ADD operation. It sends the appropriate control signals to the ALU, or arithmetic logic unit. The arithmetic logic unit, or ALU, is the part of the processor responsible for performing arithmetic and logical operations. Based on the control signals generated by the control unit, the ALU can perform operations such as addition, subtraction, comparisons, and OR operations on the input data it receives. Now ALU receives the values read from T0 and T1. Suppose T0 contains 5 and T1 contains 10. The ALU performs the addition and produces the result, 15. At this point, the execute stage is complete. The processor has computed the result, but it has not yet stored it anywhere. Next comes the memory stage. For an ADD instruction, no memory access is required. Instructions such as load word and store word would interact with data memory during this stage, but arithmetic instructions simply pass their result forward unchanged. The processor then enters the final stage, writeback. During writeback, the result produced by the ALU is sent back to the register file. The destination register field extracted during decoding told us that the result should be written into T2. As a result, the value 15 is written into register T2. The instruction has now completed execution. Starting from a memory address stored in the program counter, the processor fetched the instruction, decoded it, read the required registers, performed the addition, and finally stored the result back into the register file. Meanwhile, the program counter had already been updated to point to the next instruction, allowing the entire process to begin again for the next instruction in the program.